Everyone. I'm just going to be talking about the harmonics and interharmonics, how it applies in the real world with AC power. So kind of the topics we'll be covering today is core functions of the AC source, then go into the importance of harmonics and interharmonics, a bit of math, probably not so much, but just general understanding of how it's calculated, and then also go over application examples and how it's used in the real world. So as many of you know, power sources and loads provide control, repeatability, and reproducibility. Compliance and certification relies on clean, repeatable, and reproducible power. If you don't have that, then you will have distortion, instability, poor simulation, and that leads to false passes, false fails, and delays in your testing. So one thing that we think is very important, the heart of compliance testing, is the AC power source. You can do many different types of tests. So tests like voltage dips, interrupts, surges. They can be a part of harmonics and flicker testing, conducted emissions and immunity testing, and can be used for compliance and pre-compliance tests. In the real world, AC waveforms distortions vary quite a bit. There's a lot of different types of distortion, so DC offsets, voltage fluctuations, you can have dips and interrupts, notching, noise, you can have oscillation or ringing, harmonics, interharmonics, frequency variation, and power surges as well. So these are things that we see quite a bit in many different industries. So with EV and automotive charging, with the EVSEs and then the onboard chargers, sometimes there could be some interactions, or there could be harmonics or less than ideal conditions. Same thing in aerospace. These complex systems can introduce harmonics. In EMC labs, with anechoic chambers and their test setups, they are evaluating different types of emissions or immunity. With the grid, that's something that occurs in the facilities as well. Harmonics and interharmonics. In your home as well with appliances, these are things that you have to consider. Same thing with manufacturing. Manufacturing equipment may create these types of conditions. Grid and transformers out in the facilities, or you might just be walking along the street, you hear humming from a transformer. Those are normally harmonics, and now with data centers and large commercial buildings, they also encounter these types of conditions. We also see an increase in grid-connected applications. So this leads to a lot of different industries, and in this particular ecosystem, looking very closely into recreating these types of anomalies. So with solar inverters, energy storage system, battery energy storage systems, wind, EV and V2G, something that we see a lot of, generators and loads like home good loads. These are products in your home that also go through this type of events and testing as well. So why do we need to simulate? Why do we simulate harmonics and interharmonics? And that's because in real world situation, real world AC systems, they are not perfectly sinusoidal, and it impacts the device. So you may encounter overheated transformers, breakers tripping, blown fuses, and that results in unplanned downtime, causing downstream distortion spikes. These situations may also cause the device not to function properly or prematurely break or fail. So the intention of simulating is basically for design verification, right? So you can see how your device operates under non-ideal conditions, and also protection verification to ensure that your device does not falsely trigger due to some harmonic event or interharmonic event, and to stress test your device, to stress test your components thermally, electrically, magnetically, to really harden your devices to be able to withstand these types of events. So an overview of harmonics. This is probably a refresher for many people, but it's good to have a refresher every once in a while. So essentially what harmonics are is integer multiples of your fundamental frequency, right? So for example, if your fundamental is 60 hertz, then your second harmonic would be at 120 hertz, and your third harmonic would be at 180 hertz. And these are normally known as even, or odd. So for the second, fourth, or sixth would be your even harmonics, and then odd harmonics would be known as the third, fifth, seventh, and so on and so forth. So if you look on the right, you'll see highlighted the fundamental. So that's our 60 hertz signal in this example. And that is what we ideally want, right? But in the real world, we don't necessarily have ideal, or ideal is very hard to come by, or simply doesn't exist. So you may have in this example a third and fifth harmonic, and what ends up happening is you get the resultant, or your device sees the resultant. And for interharmonics, interharmonics are just non-integer multiples of the fundamental frequency. So again, if we have a 60 hertz fundamental, then an interharmonic can be something else other than an integer multiple, like for example 75 hertz or 125 hertz, or anything else. And these are normally generated from nonlinear transient devices in systems. And example of this is the IEC 61004.4-13, which does interharmonic testing and has these types of requirements. Next, we'll talk about how harmonics are calculated. So essentially, it's a Fourier transform. And there are many different types of Fourier transforms. Most commonly used is the fast Fourier transform. But essentially, again, real-world AC waveforms are not perfectly signed waveforms. As we saw earlier, your waveform, or your waveform that is not perfectly signed, can be broken down into waveforms, fundamental waveforms. And this formula basically just describes that the resultant waveform is basically a summation of many waveforms. And using Fourier transform, you can take a waveform that is in time domain, and then after doing the fast Fourier transform, you can evaluate it in frequency domain. So here you can see we have the waveform that was the resultant, and then using the harmonic measurement capability, we were able to see the different components of this waveform. So again, here's another view, converts a waveform from time domain to frequency domain. So here we created the resultant waveform in time domain based on our example before. And it essentially, what it does is it breaks down the waveform into frequency domain, so that we can see what is impacting the signal, and also decide plans to mitigate this, or at least you understand what's going on. So, the idea is you ultimately just want to have your fundamental. You don't want to have these types of disturbances, but in this particular case, we see that there is a third and fifth harmonic. Next, we'll talk about the difference between even and odd harmonics. These are terms that are commonly used in industry. So sometimes you'll hear, the system having even harmonics, or you're evaluating something and you only see even harmonics. Again, these are harmonics that are even, so the second, fourth, sixth, so on and so forth. And these are typically known or seen on asymmetrical loads. So it's less common, but essentially what you'll see is an unequal current in both the positive and negative cycle or in unbalanced systems. So if we have this waveform, for example, if we were to do a harmonic analysis, you can see that you have harmonic components on the second and the fourth and the sixth and so on. And if you look at the time domain, you can see on the positive side, it's a higher current than the negative side. So you can see that it's asymmetric or unbalanced. The other is the odd harmonics. So odd harmonics are, again, the third, the fifth, the seventh, and so on and so forth. And these are typically on symmetric loads. So these are produced by nonlinear loads such as power converters, variable frequency drives, and fluorescent lighting, for example. And from the time domain, you can see that it is symmetric, right? So positive and negative are kind of balanced, so to speak. And if we were to do the harmonic analysis, you'll see that the components are in the third, fifth, and seventh harmonic. So quick comparison, that's at a high level, the difference, you have an understanding now when, it's kind of referenced, odd harmonics or even harmonics and what that. Lastly, the total harmonic distortion, THD. So this is something that what it normally is distilled to. A lot of in industry basically just look at this metric. This is a common metric used to understand how much distortion is in the waveform. So I've listed the formula here, but basically what it does is it compares the energy contained in all the harmonic components relative to the fundamental. So in other terms, it just lets you know how much energy that lives outside of your fundamental frequency. So here we're looking again at a odd harmonic. This is symmetric in time domain, very distorted. And now if we were to look at the harmonic analysis, we can see again the components, third, fifth, and so on. And then we also do a calculation. So we have three. We have THD, which is the total harmonic distortion. And then again, we also separate from odd and even as well. So normally engineers are just looking at this percentage. So ideally you want it to be as close to zero as possible. Zero is probably not possible, but you want it to be as low as possible. So in this case, you can see it's total harmonic distortion is 37%. We see that it is mainly odd and very little even harmonics. Interharmonics. So basically, it's very important, particularly with the IAC 61004-13 of creating interharmonics. So these are tests that you also need to run. These are the non-integer multiples of your fundamental, and we have the ability to create it, but also we also have the test sequences to run these particular types of tests. All right, application examples. So basically best practices for harmonics and interharmonics: understand the waveform, understand what you're trying to create, or understand what you're seeing. Then having the right tools. So either if you want to create, if you're using a source, creating the voltage with harmonics, or load current with harmonics, pick the proper equipment that allows you to do these things. And then of course having the right tools, so user interface controls, having a waveform editor, measurement capability, doing the calculation, doing the harmonic analysis for you, and having flexibility is very important. So you can see on the right, I created both of these waveforms, the both even and odd, with our waveform editor and waveform generator. Similarly, for creating interharmonics, it can be done really simply. From our drop-down menu, you can see that there's an interharmonic in control, where you essentially just select the frequency that you want and select an AC voltage. So in this case, for generating odd harmonics, what I did was use our harmonic generator, and then I just added harmonic components and the percentage that I wanted to introduce, and was able to recreate that. With the even, I needed to create asymmetric waveform, right? So what I used in this case, I used the editor, where I had a very high positive, or normally positive side, and then on the negative side of the cycle was the amplitude was reduced to create that unbalanced system, thereby creating even harmonics. And here's an example from a customer. So in this case, they are wanting to test EVSEs. EVSEs are basically chargers. And in this case, to recreate that, I used the waveform automatic generator of the harmonic content creation. So this customer had a test plan. They knew and understood what they wanted to do. They wanted to create this voltage waveform. They had the harmonic components and the percentage amplitudes and phase angles as well. So we were just really simply just enter those values into the harmonic table, and we were able to accurately recreate that with our source. So here is the waveform that we created, and we viewed it with our built-in oscilloscope function. So all this is done within the SmartSource suite. So as many of you know, this is our proprietary web-based interface with remote control. So it allows you to create all these different waveforms, control at any time. There's no drivers needed. You don't need to do any preparations in your laptop. Basically just connect to the instruments, open a web browser, and enter the IP address, and you'll be able to control the instrument. So it increases productivity, very user friendly, intuitive, and it's really optimized to enable engineers to create these different types of conditions that they want to recreate. And that's it. Thank you very much for your attention. Well, everyone, so for the second part, just